All right, started back up. So, test on Wednesday. Uh, so, uh, time is going to be expanded. So, I'll come here before. So it's 2 o'clock here. Is that good enough for you guys? You don't have to show up at 2. So, but I'll be here at 2. So, you can show up at 2. If you show up at 3, there's no penalty for that, and you can stay as pretty much as long as you want. Oh wait, but organic's coming. Organic's coming after, so we can relocate to the Astro Lab until 6 o'clock. So that's when Astro Lab starts, or maybe 5:30 because Dr. Shi will have to set up. Well, whatever gets busy. If you need more time, I'll find a spot. There'll be places somewhere. Either like the library, over there, it tends to decrease in population about that time. It depends on how many of you are. If it's like 1 or 2, I can throw you in my office. But anyways, we'll sort it out on the fly. Does anybody have any questions about the test before we start? No questions. So today we're just going to go over. This is also, so I'm recording this. I'll put it on YouTube. It'll take me about an hour to digest the video because I have to spin it down, and because it's gonna be like 2 gigs and it doesn't upload very well to YouTube from that, so I got to spin it down to an MP4, and I'll upload it. It takes a while to do all that, but anyways, I'm just gonna go over and explain each problem. So feel free to ask questions. Okay, so first one here, and again, this is also on LaLima, an abridged version. The equilibrium constant is given for one of the reactions below. Determine the value of the missing equilibrium constant. So it's the first one. If you compare the first one and the second one, it's doubled. And when you double a reaction, you actually square the equilibrium constant. So something raised to the n, a factor of n, you raise to the n power. So this new is just 1.46 squared, whatever that is. Do you want me to do the calculation? It seems like everyone wanted me to do the calculations. Or is the setup good enough? What's that? Setup's good enough?
Yeah, do the calculations for what?
Do you want me to put one? You want me to write 1.46 squared to figure out what that is? Okay. All right. Just a setup. Okay, good. My brain will be saved. Okay, the delta n for the following reaction. So the delta n. This is n final minus n initial. So this is 2 minus 1. There's 2 moles of gas at the end, and there's 1 in the beginning. This equals 1. So, okay. Does anybody have any questions on how to do this one here? Questions? Okay. Consider this reaction equilibrium. What effect will be reducing the volume of the reaction mixture have on the system? So to me, when volume goes down, that's the same thing as increasing the pressure. I think of I think of it in terms of pressure. So decreasing the volume means increasing the pressure, which means we're going to shift towards the lower number of moles. So shift toward lower number of moles of gas. So the system, so if you decrease the volume, the same thing as increasing the pressure, the system wants to shift to contract, to form fewer moles of gas to counteract the fact that so it's going to, doing lower moles of gas will lower the pressure. So if the pressure goes up, it's going to try and lower the pressure. And on the left side, you have 3 moles, and on the right side, you have 1 mole, therefore you shift right. So, is that one? Is that making sense? Questions on this one? Please do not be afraid to ask questions. Nope. Okay, so consider the following reaction equilibrium. What effect will increasing the temperature have on the system? So don't get these wrong because they're the easy ones, right? So the conceptual ones, these are the easy ones. So this is exothermic. So heat is a product, and upping the temperature means upping products. So you shift left. So in this case, the reaction is exothermic. So increasing the temperature means you're adding a product to the system, and when you add a product to the system, you shift left back towards the reactants. So, does that make sense? Questions with this one?
So like, if you're adding heat, it would shift to the left.
Because this is exothermic. Oh, I'm sorry, wait, this is endothermic. Jeez, I'm dumb. I'm sorry, this is endo. At least it's going to be recorded for everyone to know. Oh, jeez. It's spring break. Jeez. Yeah, negative is exothermic, positive is endothermic. Okay. Mike will join the conversation now. To show you how simple you can make a dumb mistake in front of everyone. And they all laugh. Okay. So, questions with this one?
How did you know this?
Because of the positive sign on the delta H. Negative is exothermic, and positive is endo. Because positive means the heat is flowing into the system, negative means that the heat is flowing out of the system.
Wait, could you repeat that one again? That last part?
Positive delta H means heat is flowing into the system, and negative delta H means heat is flowing out of the system. Heat flowing into the system is endothermic, so inside. Heat flowing out is exothermic, heat flowing outside. Other questions? Chantel's keeping me honest. Okay. All right. Consider reaction phosgene, equilibrium of carbon monoxide and chlorine. Reaction mixture initially contains 1.6 molar phosgene, that's ClCl2. Determine the equilibrium concentration of carbon monoxide at the Kc. The reaction is 8.33 times 10 to the minus 4. Calculate this based on the assumption that the answer is negligible compared to 1.6. Okay. Actually, phosgene is green. I'll do green. Can you see green? Yeah, you can. Okay. ClCl2, equilibrium, CO2. Initial change, equilibrium, 1.600. So, where do we go? We shift right. Equilibrium 1.6 minus x, x, x. Kc equals CO, Cl2, CO, Cl2. What is it? Kc, okay. What's that? So as indicated, you can disregard that x. Can you, I guess you can't see that as well. I shouldn't have picked green. So we get 8.33 times 10 to the minus 4 is approximately x squared over 1.6. So that means that 8.33 times 10 to the minus 4. So multiply both sides by 1.6. 1.6. And then this equals x squared. And you can take the square root of both sides. Take the square root of both sides to get the number x. So what else is this? And x is in fact the equilibrium concentration of carbon monoxide. So we can just, the answer is just x. Okay. So recap on this one. That reaction there, COCl2 equilibrium CO plus Cl2, initially has 1.6 molar COCl2, also known as phosgene. The Kc is 8.33 times 10 to the minus 4. What is the equilibrium concentration of CO? In this case, it's going to be x. But so write the initial change equilibrium, initially 1.6 molar COCl2, no products. So we shift right, lose one extended reaction of COCl2, gain an extended reaction each for carbon monoxide and chlorine. Then equilibrium 1.6 minus x, x and x for the products. So the Kc are the products over the reactants. So the products carbon monoxide, chlorine over COCl2. The Kc given to us is 8.33 times 10 to the minus 4. So plug in the values from the ice chart. X squared over 1.6 minus x. And we can discount that x, so x squared over 1.6. Solve for x, and whatever that value is there, and that's also it's equal to the equilibrium concentration of CO, which is what we're looking for. Questions with this one? So those of you that came in late, I'm also going to post this on YouTube, and there's also a shorter video on LaLima. So, okay, questions? Need any more explanation about anything? Okay, determine the value of Kc for the following reaction. If equilibrium concentration are as follows. 0.13 molar hydrogen chloride, hydrogen iodide, 5.6 10 to the minus 16, chlorine, 0.0019. So the Kc, this is products. Now the problem with iodine there, the I2, it's a solid, so it's not included in the equilibrium constant. So you just plug in the numbers, and don't forget to square HCl and HI. Okay, HI, so 5.6 times 10 to the minus 16 squared, 0.0019 for chlorine all over 0.13 squared. So, I mean, just looking at this, it's going to be E, because the minus 16 squared is going to be huge. But, okay, questions with this one? So this one is just using the definition of equilibrium constant, and then putting the numbers in, and it's just straightforward. Questions with this? Nope. Okay. A solution with a hydroxide ion concentration of 4.15 times 10 to the minus 6 molar is blank, and has a hydrogen ion concentration of blank. That is in fact acidic. I'm sorry, that's basic. You can do it by calculating the pH if you want. But if it's greater than 10 to the minus, if the hydroxide ion concentration is greater than 10 to the minus 7, it's going to be alkaline or basic. So, in the hydrogen ion concentration, well, man, that rain is falling down. Or is that this? That's the wind, isn't it? I don't see that much rain. Or is it, oh, I see the rain now. It's both. Man. All right, so you can do it a couple ways. Hydrogen ion times hydroxide ion is 10 to the minus 14, which means then hydrogen ion is equal to 10 to the minus 14 all over hydroxide ion is 10 to the minus 14 all over 4.15 times 10 to the minus 6. Which is 2.41 times 10 to the minus 9. So that's the hydrogen ion concentration. If you want, you can do the pH. The pH is 8.61. If you really, really want to go and do the pH, pH is 8.6. So, but if the hydroxide ion concentration is greater than 10 to the minus 7, it's going to be alkaline or basic. So it's that one. So questions with this?
What?
What's that?
You said it's 10 to the minus 7.
So if the hydroxide ion concentration is greater than 10 to the minus 7, it is basic. If hydroxide ion concentration is less than 10 to the minus 7, it is acidic. If it equals 10 to the minus 7, it's neutral. That's just because like the pH POH thing. So
it's acidic, it's less than 7?
yes. Oh, yes. Wait a second. pH, if the pH is less than 7, is acidic. If the POH is less than 7, it's alkaline. So, but most everyone in the world does pH. No one except for weird chemistry teachers talk about POH. Other questions with this one? Oh yes, the one that made a student cry. Which one of the following salts, when dissolves in water, produces the solution with a pH closest to 7? So, for this one, so you look for a strong acid plus a strong base. And you have two choices that fit this. We have the potassium bisulfate or potassium hydrogen sulfate in cesium iodide. Now, it's not this one. It's not the potassium bisulfate because HSO4 minus is an acid. So it is D because it is the neutralization reaction of cesium hydroxide and hydrogen iodide. Or hydroiodic acid. So, this make sense? Questions with this one?
I wouldn't know.
What's that?
I wouldn't know that.
Okay. Well, now you know.
Why are you looking for a strong acid and strong base specifically?
So, if you have a a strong acid and a strong base, as long as the strong acid is not sulfuric acid, it will always produce a neutral salt. So if you have a couple choices here. If you have
Oh, because
the
pH.
strong acid plus strong base, this is a neutral. If you have strong acid plus weak base, this is going to be an acid salt. If you have a weak acid plus strong base, this will form a basic salt. And if you have a weak acid plus weak base, you have no idea what you're going to form.
I just realized you said pH closest to 7, which is neutral.
Yeah.
So
So the way I always remember it is the strong acid is so strong that it makes the weak base, turns it into an acid. That's not proper. The real reason is because the weak base, the conjugate acid of the weak base makes the solution slightly acidic. That's really what's going on. But I just remember it. I just like this picture of them fight in my head. And someone wins.
that's fair.
So cesium iodide, they fight and it's a draw. They knock each other out. But strong acid and weak base, the acid punches the base and the base goes down like, ha, you're an acid now. So, but okay. Questions with that one? Yeah.
Which strong base makes up T?
Cesium hydroxide. So the strong bases are all going to be the hydroxide salts of the alkali metals and the alkaline earths. So if you see any of these, not hydrogen, but any of the alkali metals, alkalis and the alkaline earths, those are all the strong bases. There's even in the name, the alkali metal, alkaline earths. Alkali means basic. So, other questions? Okay. Okay, pH of a carbonic acid solution. All right, so this one here, it's a diprotic, and I'll let you in a little hint. You don't have to worry about any other polyprotic acids beyond the first hydrogen, because it'll be negligible, with the exception of sulfuric. And I'm not asking you a question about sulfuric acid, but I'll go ahead and prove it for you now because I think we have the time. Especially, I've only been talking for 22 minutes, and we're almost halfway through the test, so we got lots of time. Okay, so it's a two-step equilibrium process. So it is H2CO3, equilibrium, hydrogen plus bicarbonate. So initial change equilibrium. So 0.08, 0, 0, shift right. 0.08 minus x, x, x. Ka1. Ka1 is going to be hydrogen ion, HCO3 minus, all over H2CO3 equals x squared over 0.08 minus x. And I can discount that x. Equals x squared over 0.08 equals 4.3 times 10 to the minus 7. So let's go ahead and calculate this one out. So x equals the square root of 0.08 times 4.3 times 10 to the minus 7. So x equals 1.85 times 10 to the minus 4. Okay. So now what you do the second time is, so the second step you have HCO3 minus in equilibrium with H plus CO3 minus 2. And you have another initial change equilibrium. The difference here, though, you have 1.85 times 10 to the minus 4, 1.85 times 10 to the minus 4, 0. And you still shift right. And you have 1.85 times 10 to the minus 4 minus x. 5 times 10 to the minus 4 plus x and x. And Ka2 is going to be hydrogen ion, carbonate, all over HCO3 minus. Equals 5.6 times 10 to the minus 11 equals x, oh, that's an x squared. Actually, there's an x there. X 1.85 plus x 1.85 minus x. Oh, and the math. You'll love this math. You can discount those x's. And if you discount those x's, then the 1.85s will cancel. And x is 5.6 times 10 to the minus 11. So you have it only breaking up, so the difference 10 to the minus 11 versus 10 to the minus 4, that's a factor of 10 to the 7. That's 10 million. So it's only breaking apart like one part in every 10 million. So it's negligible. So you do not really have to worry about that part there. So that's negligible, and you go back here to x, and then so what is the pH? So x also equals the hydrogen ion concentration. So pH is minus log H plus equals minus log 1.85 times 10 minus 4. So it's that one. So you don't really have to go and do the second. So I went ahead and did the second one just to show you that it's negligible, because difference in 10 to the 7. So difference of a factor of 10 million. So with the exception of sulfuric acid, don't have to do the second step. So if you want to save yourself time in the test. So, but questions with this one? It's just like the other acids. So you have initial change equilibrium, so carbonic acid breaking apart. So initial conditions, we shift right. So lose one extended reaction of carbonic acid, gain one extended reaction of hydrogen ion and bicarbonate ion, and then add them for the equilibrium. So 0.08 minus x, x and x. And then the equilibrium constant is products over reactants. So the expression becomes x squared over 0.08 minus x. And since Ka is to the minus 7, you can discount that x if the difference is 10 to the 5. So 100,000 difference. So then we find our x to be 1.85 times 10 to the minus 4 molar. The pH of that is around 4. So, questions with this one? Okay. The weakest acid. So weakest acid is hydrofluoric acid. So the strong acids, are HCl, HBr, HI, nitric, HNO3, sulfuric, H2SO4, perchloric, HClO4. So if you remember that, I'll write them down. HCl, HBr, HI, HNO3, H2SO4, HClO4, and specifically here, not HF. Hydrofluoric acid is a weak acid. So, actually, if you really want to know, of the acids there, the strongest one is hydroiodic. HI is the strongest acid. It gets stronger as it goes down. But that's in water, it doesn't matter. That on the gas phase, it's worse. It's more reactive. HI is more reactive than HCl or HBr in the gas phase. But this is just kind of one of the points to remember the strong acids. Questions with this one? You look kind of. Everyone looks kind of sad. It's a rainy day. If it was sunny, would you be happy?
I don't know.
Okay. Determine the pH of a 4.461 molar benzoic acid solution if the Ka of benzoic acid is 6.5 times 10 minus 5. Okay, so this one here, I know it's benzoic acid, but generic acid, hydrogen acid is equal to equilibrium of hydrogen ion plus conjugate acid anion. So initial change equilibrium. So this is 0.461, 0, shift right, minus x plus x plus x, 0.461 minus x, x, x. Ka is hydrogen ion, anion over acid, equals 6.5 times 10 minus 5 equals x squared over 0.461 minus x. Discount that x. So it's approximately x squared over 0.461. So x squared equals so you can just take the square root of both sides. To get that, I'll just go ahead and do this one out. So 0.461 times 6.5 E is 5. 0.00547, which also equals to the hydrogen ion. And pH is minus log hydrogen ion. .26, which is a okay. Yeah.
I never got this about why. When you exactly do like not you only disregard the x.
Okay.
Like in what situation would you? Like I know it's when this number is small enough, but I don't know what the small enough is.
It's if it's less than 5%. For this class. It depends on what your requirement is. So, meaning a deep impact probe, the example I used in class, a deep impact probe, that's when they had a probe and they shot one probe that hit a comet. And so you had to line up, this is one heck of a trajectory shot, right? So you had to line up a rocket that shot a projectile and struck a comet. And the comets are not that big. So, and it was going across millions of miles. So if you're doing a calculation like that, you have to be extremely precise. You have to include the gravitation field of the moon, of Jupiter, of Mars, of the Earth, that kind of thing. So if you're doing a very, very close, what the heck just happened? Okay, well, it's the iPad, not the computer. Hopefully it's still recording. Anyway, so the deep impact probe it needs to be a very fine-tuned calculation. So for something that you're just doing with an instrument, I mean, like a pH probe. I mean, pH probe, unless it costs $10,000, it's going to have an error of 5 or 10%. So if you're doing something that you need to have a very, very fine-tuned thing, then you could not disregard X. But for this class, and I mean, like, it's the only time that you would need to do something that exact is maybe if you were designing something specifically for a person that had a really particular need. I mean, it's for most other applications you would just take this part of the error. But anyways, for this class is that, and the answer is about 5%, and this is done for many sciences and engineering. So discount terms, this won't be the last time you see discount terms. The E equals MC squared equation, that's discounting terms. Sorry, Jet, am I giving you the dollar answer to your nickel question?
It's just because all the times, like for the last time I took the TLC, I didn't disregard any of the X's because I didn't know if I needed to or didn't need to.
Yeah.
So I didn't know.
Well, then you don't have to, and you can just, if you have your calculator, just solve it. I mean, that's perfectly valid. But where you discount it is when you relate it to something else. In this case, so in this expression here, it's the 0.4. What you're saying is 0.461 minus x is about equal to 0.461. That's the leap of faith that you're doing there. So I mean, what about the top numbers? Can you discount that? Like, no, because if you put them as 0, then you have 6.5 10 to the minus 5 equals 0. Or you could say it's approximately equals 0, which is true, but I mean, you don't get any usable information out of that. Am I helping you, or am I?
Again, it's just I'm very confused over the last test.
Yeah. It's always when you relate it to something else. But I don't think we discounted anything from the last test, or any discount x's. Are you getting mixed up with a different class?
Oh no, it's this class.
Because we did solutions and intermolecular forces and kinetics the last class. And was there a discount x question? I don't think there was. Which test did I put in there? But okay. Oh, do you want to take this test in the Learning Center?
No, that's not what I'm asking.
Okay. If anyone wants to take the test in the Learning Center, it's fine with me. So.
Is it time? Is it
No, it's not going to be timed here either. So it depends on if you want to look at me or look at something else.
what time is it start?
Here, I'll start at 2. You don't have to show up at 2.
So if we take it at the Learning Center,
Not necessarily. If you want to take, it'll be the same. If you want to take it at the Learning Center, it'll be the day. You can, yeah, whenever you want to start it, but you have to do it in one sitting, kind of like the rules of the last test. So, I mean, if you like that better, I mean, I'd be happy to accommodate you. So, if you want to explore that, well, tell you what, if you want to explore that option, just email me. Okay, and then we'll negotiate what it needs to be done. And I'd rather you do it on that Wednesday, because then I can give the test back to everybody and release a test to everyone. So, but if there's any circumstances or something, just let me know. Other questions? Okay. So next question. Determine the Ka of an acid whose 0.294 molar solution has a pH of 2.8. So this is where you have generic acid, equilibrium, hydrogen ion plus, that's initial change equilibrium, so 0.29400, shift right, 0.294 minus x, x. So then your Ka is hydrogen ion, anion over acid, which is x squared all over 294 minus x. But what is x equal? So, but the pH is 2.8. So x equals the hydrogen ion concentration, which is 10 to the minus pH, 10 to the minus 2.8. Which is 0.0016. So you can just put that in the equation then. You just put that in there and pop out the answer. Do you want me to calculate it out? Raise your hand if you want to calculate it out. All right, we're good. So this one here, I've been training you to do the ice chart, so I went ahead and constructed one. So you're given initial concentration and the pH. You want to find the Ka. So same steps, but if you, in this case, your X value, the extent of reaction in this case is going to be the hydrogen ion concentration. You're given the pH, so from the pH you can figure out the hydrogen ion concentration. So, and then from that plug it in to get the Ka value. Questions with this one? Ooh, all right. Henderson-Hasselbalch now. Calculate the pH of a solution that's 0.295 molar in sodium formate and 0.205 molar in formic acid. So this is when you use the Henderson-Hasselbalch equation, where you have pH equals pKa plus the log of the base over the acid. So first of all, you're given the Ka. The pKa is minus log of the Ka, minus log of 1.77 times 10 to the minus 4. That's the pKa, plus the log of the base. The base in this case is the sodium formate, 0.295 all over the acid, 0.205. You just throw that in your calculator and then leave. Okay, so common questions are, how do I figure out which one's the base and which one's the acid? So the base is going to be the one that has the alkali or alkaline earth metal in front of it. So the lithium, sodium, potassium, rubidium, cesium, it's usually going to be sodium or potassium. So, because the other salts are more expensive, or they're also biologically active. you start throwing lithium salts into biological things, you can get adverse reactions. So, like, because lithium can be a mood stabilizer. Also, the other hint is which one's the acid. The acid is the one that has the extra H, and it's also the one that has acid in the name. So formic acid is the acid because it says acid in it. So that's another hint. But the other hint is it has an extra hydrogen. So acids are proton donors. That means they have an extra proton, extra H. So, okay. Questions with this one so far? This is just the application of the Henderson-Hasselbalch equation. And the only other tricky thing about this is that you're not given the pKa, you're given the Ka, but the pKa is just the minus log of the Ka. So, any questions with this? Okay, calculate the percent ionization of nitrous acid in a solution that's 0.222 molar nitrous acid and 0.278 molar potassium nitrite. The acid dissociation constant is that. So this is a common ion problem. So we have HNO2 in equilibrium with H plus NO2 minus. Initial change equilibrium. Initially, we have 0.222, 0, and 0.278. So the idea here, so common ion, the nitrite ion is common in this, so it has to be included in the equilibrium constant. Where do we shift? We shift right. Why do we shift right? Because of this 0. If you have a 0 on any of the sides, that's the side you shift to. If you have a 0 on both the reactant and the product side, then no reaction happens. But if you have a 0 on one side, the reaction will shift toward that side. So lose X, gain X, gain X, 0.222 minus X, X, 0.278 is X. So the Ka is going to be nitrite all over nitrous acid, HNO2. This equals 4.5 times 10 minus 4 equals X, 0.278 plus X over 0.222 minus X, and which is nice. You can discount this one, you can discount that one. So do you see why, Jet? No, you don't? Yeah, it's the minus 4 versus 0.2, that's the difference. That's about, it's 1,000, it's 1,000, it's 0.1%-ish. But even more important that you're relating this to, so the 0.278 plus X and the 0.22 minus X, these numbers, these X numbers are insignificant in comparison to those numbers. That's, you know, it's, right, so Donald Trump picks up a $20 bill on the ground. He's like, sweet, I have to recalculate my personal wealth now. You know, homeless guy walking on the street picks up a $20 bill, like, woohoo! I'm rich now. You know, so depends on what you're relating it to. So this is then. So then this is approximately. Approximately X 0.278, 0.222. So X equals So you have to multiply 0.222 on both sides, and then divide by 0.278 for both sides. So 0.222, 4.5 times 10 minus 4, all over 0.278. I'll go ahead and calculate this out. So 0.222 times 4.5 is 4 divided by 0.278. And this is 3.95 times 10 to the minus 4. Okay. So, now, so what? That's how much it's disassociated. So, the percent ionization, so this is equal to how much breaks off over the original times 100%. So which equals 3.95 times 10 minus 4. The originally is 0.222 times 100%. So this one divided by 0.222 times 100 equals 0.162%. Okay, so part where the students also where I wanted to disregard the x, that's a common question with that one, but that's true for several questions. Question is, how do you figure out the percent ionization? That's how much rips off over how much you had originally times 100%. So like, let's say like, well, how much percent of my body weight did I lose? So if I have 100 kilograms of mass and I lose 2 kilograms, how much body mass did I lose? Well, the answer is I lost 2 kilograms divided by 100 kilograms. I lost 2% of my weight. Right? So same thing with this. If you find out that you break off 3.95 times 10 to the minus 4 molar of in this case hydrogen ion, but that's how much in moles per liter this acid breaks apart, and it's originally 0.222 molar. So it's how much broke off over how much it was originally times 100%. Just like the other analogy with the how much weight did you lose, the how much weight you lost over the original weight. So, does that make sense? Okay. So the other thing with this, it's a common ion problem. So the common ion, in this case, the common ion is nitrite. So be sure to include the common ion in the equilibrium expression. So, questions with this one? Man, I'm fine. Oh wait, we're losing. We're gonna end at 4:15, so I gotta talk faster. Okay, how many milliliters of 0.850 molar sodium hydroxide are required to titrate 25 milliliters of 0.072 molar hydrobromic acid? So we can do probably just do dimensional analysis with this one. So let's see here, 25. Or you could also do, it's 1-to-1. It's a 1-to-1 ratio. I think even easier. So so here, moles acid needs to equal moles base. So the moles NaOH need to equal the moles HBr. And so, and you can also do this, I guess this book uses C. I'm used to using M. C1 V1 equals C2 V2. Do you use that, or do you use M? Use M for, I was always taught M. M, okay. All right, so since it's 1-to-1 molar, you can do that directly. So let's see here. So 0.085 times x equals 25. That's a 5. 25 times heat. 0.072. So this case here, you just have to divide by 0.85 to get that, and that'll give you the answers. That'll give you the answer in milliliter. But the idea here is that you need to figure out what the moles of acid equals the moles of base, and you could do it by dimensional analysis, where you figure out the. Raise your hand if you want me to do it by dimensional analysis. Okay, that will never fail. But if you want to, you could figure out, so 25 milliliters of 0.072 molar HBr. That will give you so many moles of HBr, and then you have to have that number of moles of sodium hydroxide. But then you would take those moles, divide it by the concentration. It'll give you the volume. Of course, it'll all be in liters, so you'd have to convert to mill it back. So, but I'm avoiding trying to do that way, because then I'd have to multiply it and divide by 1,000, and I don't want to confuse people. But questions with this one? Okay. What is the pH of solution by mixing 30 milliliters of 0.1 molar acetic acid with 50 milliliters of 0.1 molar potassium hydroxide? Okay, so this is another one. Okay, so something to note, you have the same concentration. I can draw a picture. So you have a big beaker, and you pour in 30 milliliters, 0.1 molar acetic acid, and then you put 50 milliliters, 0.1 molar KOH. So what's going to happen is, it's the same concentration. You're going to have, of course, this is going to be 80 milliliters now, but these 30 milliliters are going to react to the 50 milliliters, and we have 20 milliliters of 0.1 molar KOH left over. What I'm saying is that the first 30 milliliters of potassium hydroxide is going to be consumed by the acetic acid, and you're going to have 20 milliliters left over, which means you have 0.02 liters times 0.1 molar KOH, which means you have 0.002 moles of KOH now in 80 milliliters of water. So that means that the hydroxide ion concentration, is everyone okay with my logic here, that you have 30 milliliters of acetic acid and 50 milliliters of potassium hydroxide? You throw them both in, they're going to react, and your leftover is 20 milliliters of 0.1 molar potassium hydroxide, which is 0.002 moles of potassium hydroxide. Is everyone good with that? So now the concentration then is moles per liter, 0.002, all over 0.08 liters. So what is that? I can't do that in my head. I should be able to. Okay, that's 0.025 molar. And I like to do the POH. The pH is 14 minus the POH. So and if you put that in your calculator, you get 12.40. So, and the POH is the minus log of the OH. So that one looks like a really crazy problem, but it's not that hard. Well, if you think about it in kind of I have to think of it in terms of like, oh, you're actually pouring them together. And then it's actually a limiting reagent problem. So it's a limiting reagent, and then the excess, the acetic acid is the limiting reagent, and you're left with extra hydroxide, and then the hydroxide shifts the pH. So, does that make sense? Questions with this one? Okay. Calculate the solubility product constant, also known as KSP, for silver sulfite if the solubility of silver sulfite is 4.6 times 10 minus 3 grams per liter. Okay, so the problem with this one is, I already used Boyle. I haven't used the screen. So we got to change grams per liter to moles. So, okay, so let's see here. Ag2SO3. Okay, what is a molar mass of that? So silver is 107.87 times 2 plus 32.06 for sulfur plus 3 times 16 for oxygen. 107.87 times 2 plus 32.06 plus 3 times 16, and we get 295.8 grams per mole. And so now, let's see here, 4.6 times 10 minus 3 grams per liter times mole Ag2SO3 all over 295.8 grams Ag2SO3. Okay. This is equal to 1.56 times 10 to the minus 5 molar. So, and it wants the KSP, so Ag2SO3 equilibrium with Ag plus SO3 minus 2. So initial change equilibrium. We're gonna, oh wait. We have 0 of these, 2 solubilities, solubilities, equilibrium, 2 solubilities and solubilities. KSP is going to be silver ion squared, so 3 anion the first equals 2s squared s equals 4s cubed, and then this is the molar solubility. So then you take that number and you just multiply by 4 and cube it, and then you get the answer. So the difficulty here is probably converting grams to moles. So, recap of this, what's the KSP? KSP is solubility product constant. So, you have to go and write out the equilibrium expression. Well, you have to write out the, I didn't even write out the equilibrium expression. I knew I'd have to calculate the molar solubility. Write out the equilibrium expression, you find out that the KSB is 4 times the molar solubility cubed. You're given the molar solubility in grams per liters, so you have to change that to moles per liters. And once you do that, just throw it right back in. Questions with this one? Okay. Can you see brown? Yes, you can. Okay. Calculate the molar solubility of magnesium hydroxide at a pH of 12.5. So MgOH2 equilibrium with magnesium plus 2 plus OH minus. Initial change equilibrium. Initially, this is 0. So pH of 12.5, that means that the hydroxide ion concentration is 10 to the minus POH. So 10. So this is equal to 10 to the minus 1.5 equals 0.0316. So when you do this, this is 0.0316 change plus solubility to solubility, solubility, 0.310. So the KSB, we give it to you, what is it? 5.6 times 10 minus 12. So again, you can discount that 2s. So that means our molar solubility, oops. Whatever that number is. It's either C or probably C, I think. But okay, so recap of this one: molar solubility. Basic solution. The trick here is that it's a common ion problem, and the pH being 12.5 means you're going to have a specific hydrogen ion concentration. That does not change. So that's the other thing. It does not change. So it does not change. It's not going to change at all adding it. So it's buffered at that, and then you with the KSP value you can solve for the molar solubility. It's a really small number. So questions with that one? I think I'm losing you guys. Oh, good. These are related. Ha. Score. Okay, what is the molar solubility of barium fluoride in water? So, BaF2 equilibrium with Ba plus 2 plus 2F minus. Initial change equilibrium. Initially 0, 0 plus solubility plus 2 solubilities. Solubility, 2 solubility. KSP is going to be barium plus 2, F minus squared. Equals, so S, 2S squared equals 4S cubed. So this is 1.7 times 10 minus 6. So 1.7 times 10 minus 6 all over 4. The cube root is equal to the molar solubility. Okay. We did these in class. Is anybody have any questions with how I did that? Okay, so same idea. Same idea for this one. The exception being is that it says barium fluoride N.75 0.75 molar lithium fluoride. So this is 0.075. And the most common question I get is, how do I know it's a common ion? Because they both have Fs. They both have Fs, therefore it's a common ion. So plus 2 solubility, 0.075 plus 2 solubility. Same thing. 1.7 times 10 to the minus 6 equals the KSP equals barium plus 2 F minus squared. So equals solubility plus 0.075 plus 2 solubilities. You can discount that. It's that plus 2s because of negligence. You can neglect it because that's tiny. Equals solubility 0.075 squared. And then 1.7 times 10 minus 6, 0.075 squared is equal to the molar solubility. And we're done. With 2 minutes to spare. Okay, so these are similar. You have the solubility product constant, so number 19. This one here, there's no common ion, so you start with 0 of both barium and fluoride, and shift right. The most difficult part is don't forget to square the 2 inside the 2, so it's going to be 4 molar solubility cubed is when you write out the expression, so don't forget that 4. And in the second one, it's a common ion, so include the common ion and the initial conditions, and discount the terms. In this case, you can discount the 2s and the fluoride, so it'll get rid of that term, and then makes the calculation much easier. It's actually, number 20 is an easier question than the 19. So questions with this one? Okay, so I'm gonna go ahead and stop the recording, and then I can